So, now we will follow up with comfort ventilation, right. What was comfort ventilation? Local velocity at some level of the human level, which will provide evaporation or removal of heat by convection or by evaporation loss, So, sweat generated would actually be removed. So, that requires air velocity, and now we can find out desirable air velocity knowing the temperature and relative humidity. How? Remember TSI, and TSI formula was dry bulb temperature, wet bulb temperature minus 2 under root, right. So, therefore, if I know the TSI comfort range, so either put it to 30 or 34, 34 is tolerable, 30, and you know the dry bulb temperature, and either you know the relative humidity or wet bulb temperature. So, correspondingly what is the desirable velocity, you can calculate out, and this has been calculated from this one, from TSI values. Say when dry bulb temperature is 30 to 28, relative humidity you do not really require, because 28 even at 90% additional air velocity is required, not required. But if it is 30 TSI, I am not talking about, dry bulb temperature is 30, from TSI I am calculating back. So, a velocity of 0.24 meter square is fine, meter per second is fine, 0.85 meter. So, as the relative humidity increases, I need higher velocity, desirable velocity is higher. As the temperature increases, desirable velocity is higher, and this I mean this is 0.24, 25 etc. This you can actually cannot achieve, it is too high. 35 degree dry bulb temperature, 90% relative humidity, beyond acceptable limit, actually. There are other aspects also. If your velocity is too high, you start feeling a kind of a discomfort also, because supposing you are standing on a gust, or skin tends to be too dry, papers fly away. So, all this kind of discomfort is there. So, this is 30% relative humidity, 35 other, you have to provide other means, right. Maybe local fan even, but its velocity should not be too high. So, some partial, but other means should be utilized. So, this desirable air velocity can be obtained. Second issue is critical height. Where do we want the velocity? Because velocity at all level may not be same. This is the floor level, let us say, this is the ceiling level. Now, you want velocity at certain level. Supposing I have openings at this level, both inlet and outlet, air will enter like this and go away, velocity still here will be 0, but you will have still meter cube per second flow will be still high, but that does not mean you will have comfortable situation, because comfort ventilation velocity may not be high at the desirable level. What you need is the critical height is sitting on the chair is 0.75 meter, it is actually the head level, because if you can remove the heat from the head level, human head level, that keeps you more comfortable. The air I mean the blood circulation to the brain. So, head has to be, and even you might see that whenever you are jogging or doing something, you will have a lot of sweat here. So, naturally try to, sitting comfortable is 0.75 meter level, computer should be kept, CPU should be kept cool. So, that is very important. On bed obviously somebody is lying 0.6, and on floor sitting children, school children, like or like nursery level children, not sitting on floor, but small chairs and all that. So, that is around 0.4 level. So, maximum air movement should be at 0.85 critical height level, 0.85% of the critical height level. So, you can see that this is so it should be at the level somewhere close to the floor, not too high. So, that is critical height. So, comfort velocity should be high there, flow can be there through anywhere, which will remove the heat, provide even possibly fresh air, because like if it is hot air, it will go up and then get out. fresh air supply also will be, but this, so if you provide all opening here at the top level, actually no velocity there, it is not useful from velocity point of view. But if you provide somewhere there, there is a seal height, and if you provide somewhere there, then it has a tendency to. So, the seal height is very important. Seal height of around 0.9, 0.75, 0.8, they are good, right. These top level ventilators, they do help in removing some heat, but not necessarily providing higher air velocity at the floor level. If you have something like this opening and that, then it is fine, but this will be in shadow, this will be shadow areas, this will be shadow areas. This is again fine, inlet here, outlet there. So, height of the ceiling height, seal height is important. I mean seal height is important with respect to floor, and air movement must be directed at critical level. Window sill is this is the window sill, this is called, this is the height, you know, where the window starts. So, that height is important, or opening, like, so top level ventilation may take some heat away, but just alone at those positions won't make much of a sense. But some here, some there, that might make sense, because some flow might be, it might spread over the whole height. If I have one window at the lower level and then there is a small ventilator at the top. On the other side also top I have got one ventilator and a window below, then the flow velocity everything will be high, because it will get directed, you know, mixture of these two, combination of these two, then this is more useful, because you have now increased the effective opening area, right. So, in plan if you look at it, if you know, it can be something like this, depending upon where it is, parapet wall if it is there, they direct. So, you can use louvers to direct, air movement must be directed at critical level, as I said, and if you have louvers, so there could be different varieties of flow actually. There will be some shadow portion depending upon how you have located those windows, and some more diagrams showing the same. If I have a louver, otherwise it was flowing like this, supposing I put a horizontal louver, you know, horizontal louver, or the one I was talking about, rotating one. These were there actually earlier days, you would have seen the windows, or Venetian blind you can actually close in horizontal, you know, it can open and close. But supposing I have something in the horizontal plane, similar one, they will direct the wind. If it is in this inclination, then it will direct it. If it is like this, the sunshade with some opening, it will direct like this. So, they can be utilized to direct. Similarly, you have got lot of fins here, horizontal fins up to 15 degree up, keeping 15 degree up, 30 degree up. So, if it is inclined like this, they will direct upward. If it is 20 degree, it is something like this, 15 degree down, then put it down. So, depending upon the angle of those fins, they can direct, right. So, for single window maximum available velocity is only 10% of outdoor velocity. For single window maximum available velocity is only 10% of outdoor velocity, 10% of outdoor velocity, right, V0. So, outdoor velocity we are calling it V0, it is only single window will give you only 10%. For windows on both sides, windward and leeward, let us say indoor velocity is Vi, average indoor air velocity I am talking of, and whenever we are mentioning this, we mean that we would rather like to keep it, we are talking in terms of the critical 0.85 critical level, the useful level. So, velocity at the useful level, actually that is what we should be interested in. So, this velocity is a function of the fenestration area as a part of, you know, as a percent of floor area versus the available wind velocity. Supposing I have got fenestration area, that means total opening area is AW, all, or AF, let me call it, all fenestration area, and floor area is AFL, floor area. Then this is percentage. Now, you can see that if you have for 50%, then this goes to about 40% V0. That means, your V0, you know, velocity, indoor velocity Vi, average velocity will be 0.4 times outside velocity, air velocity inside will be 0.4 maximum. 50, you know, floor area you have the floor area. So, this is the floor plan, this is the floor area, the fenestration area, total window areas If it is about 50%, 50% of it, you get about 40% velocity. So, you at best outside air velocity you get only 40% of it, right, at any moment of time, not more than that, generally not higher than that. So, this is from good old days wind tunnel studies, right. People would have validated the wind tunnel studies and CFD models. If not, one can do that a little bit, and you can actually generate these days huge set of curves or similar sort of thing, design curves for first design. Detailed design can later on be done, anywhere if you want to look into the air movement. So, this was there from wind tunnel studies. In fact, this work comes from CBRI's work. This is there in SP41. This comes from CBRI's work, in fact early works of CBRI. SP41 is there. Then V.9 and then there is a correction for seal height correction. Now, when they did this experiment, they kept the seal height, this velocity was measured at seal height level s equals to 0.9. Seal height level s equals to 0.9. 0.9 meter was the starting point of the window openings, starting point of the fenestration openings, right. So, they started from there, and then if this is different, then they suggest a kind of a seal height correction. So, if 0.9 is a V.9 is found from the previous diagram, that last one diagram that I gave you, at any seal height is given by 0.072 1 minus seal height correction, where seal height correction is given as height of the seal divided by 0.9. So, if this is 0.9, then this value is 1. So, this is actually equals to 0. If this is let us say 0.72, then how much this will be? 80%, 0.8, this will be 0.8. So, this will be, if it is seal height correction will be 0.2. No, seal height is given as this is equals to 0.9. Sorry, this is actual 0.72. So, 0.72 divided by 0.9 is equals to how much it is? 0.8, isn't it? 0.8. So, 80% basically is 0.8. So, this becomes 0.2. So, 0.2 into 0.072, 0.2 into 0.072, right. So, that is what it is. Now, supposing this is more than HS, 1 meter, right, or 0.99, then this becomes negative. So, effectively velocity at my critical level, if it is at lower, still it is fine, anything above is a problem. But then remember, this is empirical formula, it is not valid for all the ranges. If s is equals to 0, this will have this will give you 1.072, which is relatively high value, but that is usually not the case, because it is infeasible sort of situation. I mean, it can be if it is all children are sitting in the floor, school level, the very village schools where children are sitting on the floor. But the point is, in that case, seal height 0 is not a practical thing, usually it will not be there. So, this correction gives you anything above, it would actually effectively reduce down the velocity for comfort condition, because it will not be directed at critical height. So, you can calculate out VIS. Earlier maximum was 0.4 V0, multiplied by now this will be 0.4 V0, and this is also a function of V0. So, you will get something in terms of V0 again, let me just write it again. You will get VIS in terms of some factor, some k multiplied by V0. So, if you know the outside predominant velocity at the time you require, you can find out what will be the velocity, average velocity inside at the level, desirable level, that is your critical level and so on. But its distribution is another thing, this is average, distribution is another thing. So, you might look into distribution also, but it also depends upon inlet and outlet size, ratio of inlet and outlet size, and these are all empirical graph obtained from experimental studies and put in there. This is all from SP41, but this gives you at least the idea, because we do not require that kind of accuracy in calculating the the velocity which I will get it, because velocity outside will keep on changing. So, if I am trying to do a kind of fenestration design which is for ventilation, which is permanent feature, all the time I am not going to get this velocity, but we get the rough idea. For example, area of inlet to area and inlet to as a percent of total area of fenestration. So, 50 means inlet and outlet, I mean sorry 100 means inlet and outlet are same. No, what is it? Area of inlet divided by percent of area, total area of fenestration. So, only inlet, this is only inlet. 50 means inlet and outlet area is more or less same. So, if you see 40 slightly inlet is slightly higher, you get better coefficients, efficiency is better coefficient, efficiency is more, and what is efficiency? Efficiency has to be multiplied actually. So, efficiency is multiplied, this efficiency is 0.6. So, whatever you have got earlier, I said K multiplied by V 0, that is what you got after sea light correction, that should be multiplied by this efficiency. So, it becomes somewhat still less depending upon inlet and outlet areas. When they are equal, it is more efficient, this is still 0.9 or so, but it hardly goes to 1, still there is some reduction. So, that is what so efficiency you can actually approximately get. So, it is preferably inlet and outlet area should be nearly same, or inlet should be actually about 40% of 35-40% of the outlet area. In other words, something like this, if this is my smaller, slightly smaller window area. So, this inlet area, direction of window is like this, should be slightly smaller than outlet area, then it gets distributed better, average velocity is somewhat better. So, this gives you some idea, right, some idea how you do it, right. But then root mean square deviations, if you see, because I talked of average so far. So, deviation, I can find out velocity at every point minus the velocity mean, square it up, sum it up, divided by the number of data points that I have taken, that becomes root mean square deviations. This varies maximum at 20% inlet, 20% inlet, at 40% this is about 10% deviation, 100% anyway velocity itself is low. So, deviation is also rare. So, deviation is 40%, you find deviation is reasonably low, value is relatively high. So, typically one might put it, if you have a prevailing wind direction known, particularly in the condition when you want natural ventilation to occur, tend to keep the inlet area something around 40%, close to 40, but should not be too different, and deviation, standard deviation, variation also is less, because distribution of the velocity in the whole room, if I have, this is my room, let us say, and I divide it into sort of rectangular portions and find out the velocity everywhere, right, rectangular grids, and find out the velocities, grid and find out the velocities. These velocities, deviation of this one from the mean, square it up, sum it up, divided by number of grids you have, that will give you root mean square deviation. So, this distribution all over the place is good, it is around this also, it is around 10% deviation, root mean square deviation is 10%. That means, every corner you are getting some air movement. I mean, you can understand this looking at it physically, For example, if I have inlet area somewhere there and outlet area somewhere there, air movement will be like this, no? It will try to cover most of the areas. There will be some shadow corners, but 40%, but then it has to is also related to total fenestration areas, area of the opening related to fenestration areas. So, if I have distribution will be more, but if it is small sized windows, they will just simply go straight. Window outlet is slightly more, it will tend to spread and distribute and then go. That is why this variation you see is somewhat less. So, that is keeping that some sort of an incident angle. There are some corrections, in fact, there are some 9 tables in SP 41, and you can go on adding those corrections one after another to approximately calculate the average inside velocity that you will get, knowing the outside velocity. So, there is another for incident angle correction, inlet greater than outlet, this value is 1, right. if it is for 45-degree incidence, this is good. For normal we talked about. For 45-degree angle, if inlet is greater than outlet, because it will drag in this manner, it will drag it, 45-degree inlet, it will drag inside and then distribute. It will drag inside and distribute. So, 45-degree angle. Inlet equals to outlet 0.8 to 0.25 depending upon the floor area, percentage of floor area, if it is 45-degree incident angle. Normal we talked about, now we are talking about 45-degree incident angle. And inlet smaller than outlet, because if inlet is large and outlet is small, 45-degree angle, this would actually distribution will be, shadow areas will be more actually. So, that is what it is saying, it is around 0.7. So, this is a correction for you multiplying factors are like this, if it is 45-degree angle of incidence. Then it says relative location of windows, there is a huge table, I just picked up a portion of the table from SP 41. If I have window locations facing each other, no correction. These corrections are additive corrections. So far all the corrections are multiplying. These are additive, plus 10%, minus 10%, reduce the value by minus 10, increase the value by plus 40. So, window located here, 0 degree normal incident, no correction, 45 degree, no correction. Same window location, same another window location here and there, maybe red color, let me just use red. Maybe window locations, no, it is not color, something like this. So, 45 degree plus 45 degree means it might actually distribute the window in this manner, and 0 degree there will be reduction. So, window locations. So, there are several such window locations given, and again these are based on local small wind tunnel studies from where they actually got those tables done long back, right. So, change in V, percentage of V, this much percentage of V would be changed, that means minus reduce it by 10%, increase it by 40%, etc., etc. Relative location of the window in a single room. There must have been some window here, some window might have been like some window, this was face to face, one is face to face, another is two and and maybe other only these two walls, we are talking of two walls, one at the center, one at the corner, something like that. There are series of combinations, I have taken only 3 of them. There are lot more about number of them actually, there are more. I have not taken that, I just, because you can always look into it and find it out, but I am trying to explain what this means. Supposing you want to look into, how you look into it. So, that is what it is. Huh? Yeah, experimentally determined. They determine experimentally in wind tunnel studies, empirically, no equations or calculated basis, no calculation is difficult, because coefficients will always come and this is far more complex. So, today modern day I want to go for CFD analysis straight away, but not for single room like this. You can simple single room like this, you can use the same SP 41 concepts. Effect of louver, that is again there is another table, and this is also additive, delta V. Horizontal sunshade they will reduce down, because they they tend to direct the wind in a different direction, not at the critical level. L type they might increase, improve at 45 degree angle and 0 degree angle, 2 cases. Box type no correction, multiple horizontal something like this, multiple vertical something like this. So, these are correction in delta V given for 0 degree and 45 degree angle of incidence. For type of louver, sunshades for example, this is horizontal sunshades. So, I can have L type of louver or horizontal sunshade, box type, we talked about this egg crate and all those. So, some of those are how they change, that is given. Veranda will have something different, veranda will have something different, veranda will have something different. Effect of veranda, they will have something different. Open on 3 sides, this is what you find in northeast or maybe Kerala quite a bit, like you will have you have something like this, roof will look like this, something like this, right, and you might have, this is how it is, this is how it is, right. So, this is a veranda, and if it is open on 3 sides, windward and leeward, then it might improve the situation. Open on 2 sides, windward and leeward, it would be something like this. Open side parallel to the wall, that is this is open parallel, this is the wall, it is open this way, this is open, these are closed, right. Open side parallel to the wall, open side parallel to wall in the windward direction, and that is in the leeward direction. Supposing wind direction is like this is the case, and another case wind direction is like this is the correction. Open side normal to the wall, that is these are the sides which are normal to the wall. This is my wall, this is my roof, this is my roof, this is my roof, this is the wall, I have a veranda here, right. This is normal to the wall is this side. If it is open, then you get these corrections minus, and if this is open, then you get better situation, and if it is on windward or leeward, it will again depend upon that, right. So, people provide veranda in those areas, maybe both sides, but usually not on both sides, usually on the front side where people enter into the house. Traditional housing, if you see, where people enter into the house, there they provide veranda. Sometimes they cover it up front portion for privacy, but if you cover it up for then you will have this kind of effect. So, it is a step by step multiplicative correction. First one we had for fenestration area as a function of floor area, inlet to outlet area, number 2. Number 3 was related to sill height. Sill height was first was sill height, then area of the fenestration, then was this one. These are all multiplicative. After that, when we started with the sunshades, they are all, or location of the window. Started with the location of the window, the position of the window, those are additive, plus or minus. Wherever it is written plus and minus, they are actually plus and minus. All are percent of outside V0, because that will be known to you from climatic data. So, approximately how much average velocity you are getting inside, you can actually calculate out. But it is a 7-8 steps calculation, not very complex. Look into the table and just do these corrections, that is it. Okay. Then effect of again another set of table. If you have 2 rooms, connector, effect of effect of 2 rooms, connections actually, location of interconnection. So, effect of interconnection, interaction here, this should be interconnection. So, 2 rooms like this, wind is from this direction, and there may be window here, window there, and wind is from 45-degree angle. So, this shows that in this room you will have 7.5% added, 15% added there, and something like that, and there will be some negative values also. Some cases it is not given. This, for example, this is only 2 rooms, so these 2 values are given. There are 4 rooms and there is no window here. So, therefore, no connectivity, there is no connectivity, there is connectivity only here, therefore, this is given. When you will have connectivity here also, there are windows on all places, you will have 4 values. This value corresponds to this room, this value corresponds to this room, right, for normal wind direction like that, and there has to be, depending upon the connectivity, if there is only one connection, here there are no connection, that is why you get 4 values, velocity here and velocity there. If there are there can be multiple of them. So, this is for interconnection between different rooms. And similarly, there is another table, I believe, yes, there is more of it. So, say this, same, continuing the same one. So, 2 values given here, 2 values given here, this correspond to this room, this correspond to this room, this correspond to this room, and this corresponds to this room, additive V, reduction in V. This straightaway given as reduction, this straightaway given as reduction. So, one can this is also reduction, location of intermediate door, one intermediate window, intermediate doors should be, openings are usually there. So, that is how actually we can calculate. So, I think that finishes our discussion on comfort ventilation as well.